All right, first of all, hello. Hi, everybody. Welcome to the Machine Learning and AI session of the Rubin Community Workshop, also Rubin 2024. This is a breakout session with contributed talks. We will have a mix of in-person and remote talks. If you're in person, I think you know what to do. Get up here. Every one of you I spoke with, and you have a plan on whether you're presenting on this laptop or clicking on a link or sharing on Zoom. If you're remote, you should be able to simply share on Zoom. Can people on Zoom hear me?
Yep.
One thumbs up.
Yeah, we got thumbs up.
Thumbs up. Okay, awesome. I don't see the screens while I'm stationed here, but thank you. So, Lior, I'm gonna stop your screen share for a second, just for the initial announcements. I don't know how to do that. Thank you. Safer that way. Is the IT person still in the room? Oh. All right. Okay. Thank you. So my name is Federica Bianco. I'm Deputy Project Scientist of Rubin Observatory. And my co-chair is Tatiana who is a student at the University of Delaware and also working with the AP team, other production team of Rubin Observatory. A few announcements, as you have heard today, the one that is most important perhaps is that the Rubin Observatory meeting, as all the meetings of Rubin Observatory and activities under Rubin Observatory, has a code of conduct, which is designed to ensure that everybody treats each other with respect and compassion. Harassment and unprofessional conduct are not permitted. And if you experience or witness any such things, please reach out to one of the code of conduct contacts. Those are Rampal, Jill, John Franklin Crenshaw, and Agnes Forte. You have their emails here. They're also available to you on the meeting Slack. And if you know them in person, they're obviously at the meeting, and you can talk to them in person. The Rubin Observatory at large adheres to the principle of kindness, trust, respect, diversity, and inclusiveness in order to provide a learning environment that will produce rigor and excellence. And if you click on that QR code, you will see the code on conduct in full. I'm sure you don't need to because you have already looked at it and reviewed it and memorized all the important aspects of it. As part of our aspiration to be respectful of everybody's need, we have a few years ago established a system of stickers that go on your tag. So on your name tag, you might put a sticker. There might be stickers on the name tags of people around you that indicate whether or not they're comfortable with physical contact in this COVID/post-COVID word. So please respect the tags that people have and don't exceed their level of comfort in physical contact. You may also see some people wearing a social battery pin. That's not foolproof, like it slides on its own. So sometimes you see people that have a social battery that doesn't actually reflect their social battery. But the idea is you're at a meeting for multiple days, interacting with a whole ton of people, and that might drain your energy. If the person has their pin sliding to the right, that means they might not be really interested in engaging at this time with people and talk. So please respect that. The virtual participants should be muted unless they are presenting, and we have two remote presenters today. The people that are speaking here should speak in the microphones. The microphone is behind me, but unless somebody complains from Zoom, we're going to leave it here so that we don't make mess and make the situation worse. So the speakers should probably be here next to the podium, so they're next to the microphone. We're also using Slack. There is a Rubin 2024 Slack space that I'm sure you've already joined. If not, you got an email with a link to join it as soon as possible, because that's the space we will use to ask questions both if you're remote, use that to ask questions. But even if you're in person and you want to ask a question, but maybe you don't want to speak up, or maybe you don't think there's going to be enough time for your question, those questions remain asynchronously available on the Slack channel, and each session has its own Slack channel. This is just an example. Day 1, Monday, 10:30, intro to Rubin. R will be day 1, Monday, presumably 2 p.m., machine learning for Rubin. So use that to ask question, and if you're a speaker, please continue consulting that channel after the session is over and answer the questions that have been asked. Raise your hand. It's a little bit hard to track. I have my co-chair who will also try to keep an eye on both Slack and Zoom at all times. But keep in mind that it's not always trivial to keep track of all these different platforms at the same time. The agenda is set with a bunch of talks, and the talks are 7 minutes plus 3 minutes for questions. I want to ask of the audience 2 things. Actually, let me start by asking the speakers to please stick to your 7 minutes and not exceed them, so that we don't run the session over. It will be, I guess, the SAC session run over. So it wouldn't be the first session that run over, but you're on the first day. So let's set a great example and stick to the time. Also, I really want to avoid awkward 3 minutes of silence, but I will leave all the time to ask the questions. So please think of questions to ask the speakers while they're giving their talk. If you feel shy and you don't think you're going to want to ask it live in person, just put it on Slack. Our moderator, our co-chair, Tatiana, will ask it on your behalf, will read it out on your behalf, and the answer will be hopefully given. The question will be answered anyways, and then we'll see if you get an answer. I think that's all I have to say. The first talk is remote, so I think, Lior, I can concede the screen to you, perhaps. Are there any questions about the modality of the session? Oh, one quick thing. If we have time at the end, if we stick to the 7 + 3 and a couple of minutes for each poster, there should be time at the end where we can have a discussion about what are concerns and needs for applications and development of machine learning and AI for Rubin. So maybe start thinking about talking points. All right. Yes.
What they told us at the beginning of the previous session here was that all that area
that's
has
right.
microphones. So if people talk to each other, you're gonna be heard.
Conversely, if you're on that area and you want to ask a question, you have to walk this way.
It's not necessarily like you don't have to go all the way to where Federica is, but anywhere like close to there should be fine.
Yeah. All right. Now we're ready to start. Lior, can you share your screen?
No, you need to stop sharing so I can share.
Yeah, I thought I did. Stop sharing. Okay.
Oh, there we go. So can you see my screen?
Yes, and we can hear you. Can everybody hear Lior? Okay, we're good.
Okay, good. So good afternoon. So let's see. Okay, so deep neural networks, no introduction needed here. Everyone is using them, everyone is celebrating them, and now you don't need to have a PhD in signal processing to do machine learning. Everyone can do that, but that can also lead to some problems. We know about overfitting, and I sense that there is a definition to the term overfitting, and recently it's been used as like when something is might seem fishy with the neural network. We use the term overfish like as a general term that some is not right in the neural networks, but it can be more complicated than that. Here's an example from COVID-19. So what we have here, it's a data set of X-rays, chest X-rays, and we can classify whether the person has COVID-19 with chest X-ray, people that with the chest X-ray don't have COVID-19 or other conditions. So it's a really classical classification experiments using convolutional neural networks, and it was used by more than 1,000 papers that cited that data set. So we have no reason to suspect anything. But here's the thing: what we did, we took from what you see on the right, we took from each X-ray, we just took the top right 20 by 20 corner that is just have background, and you create a data set just with the background. It looks like this. So you see on the left, you see the original X-rays. On the right, you see the images that we use, just the top right background. It doesn't have any part of the body. And then we ran the experiment, and then we get, just with the blank background, you get almost the same accuracy, almost the same results as you get with the original X-ray. So these algorithms, they seem like they can classify COVID-19, but they don't really. They sense something else. You can identify COVID-19 without any part of the body. It means that they sense something else. And you may say, well, that's COVID-19 era. Everything was crazy, was really quick, and there's a lot of fake science from that time, we know. But not exactly, because it happens all over. That's the quasar data set used a lot. And the same thing, you can identify diseases just with the black background that doesn't contain any part of the body. You can still classify diseases. That's an example from face recognition. So we can build a data just from the background of the faces. We can build a data set, and we can run a deep neural network. A deep neural network can recognize a face. So it does face recognition without the faces. And that's taken from the FAIR data set. That data set was cited, I believe, the whole FAIR data set were cited, I believe, more than 100,000 times. It's crazy. Everyone was using that. And we can see that we can do face recognition without the face, seemingly, and that may not be as funny as it seems. It leads to things like this. That's from 2016. It was in the news all over the world that deep neural networks are so smart that they can identify criminals by their face image. And that is, first of all, that's not true. That's fake science. That's not true. It doesn't even make sense. But because of the social impact of that, and then it makes it more of a problem. And if MIT says that the convolutional neural network can identify spaces, who can argue with that? And that's what, and still, until just recently, I heard that in computer science conferences, people say that, like, leading figures in the field, and kind of they make it like it's not politically correct, but it's true. No, it's not true. And some of what I said are summarized in this article in Nature published a few months ago. So I really recommend, if you're a student, if you're just starting, I really recommend take the 10 minutes to read this article. Can save a lot of pain later. Let's go to astronomy. So what we did here, that's an experiment using convolutional neural network to classify between elliptical and spiral galaxies. These are kind of experiments that have been going for at least a decade, probably more. People have been doing these experiments for years. And what we have here, we use a test set. We didn't change. We used the same test set. So the universe was the same universe. But the training set, we use a training set. One time we use a training set, so all galaxies came from the same part of the sky. And then we use experiments that the spiral galaxies came from one part of the sky. The elliptical galaxies came from another part of the sky. And we trained a neural network, and every time we trained, we got a different universe. Not a lot different, but it was statistically significant different. And that's scary because there's no way to tell that. There's no way to defend against it, because even if you have access to the training set and you go over the training sample one by one, they all seem correct. They all seem clean. And still, it leads to, as we see, it leads to different results. Even though the test data are the same, the universe is the same universe, it can give you two different universes based on how you train the network. Although the training sets are all good. That's the same thing, but with photometry. Photometry, I think from SDSS, we do the photometry again. Same thing, same results. And same problem, it's just by looking at the vector that comes from SDSS, the photometric values, it's very difficult to identify those biases. We have explainable AI. Explainable AI is promising, but still underway. Some of what we call explainable is not really explainable. Some of the like attention mechanism and things like that, they don't really provide an explanation. Another problem is that many of the explainable AI tools are themselves not explainable. So instead of making it more simple, it adds more complexity to the problem. And that's it. That's a very short summary of a long topic.
Thank you, Lior. I'm really glad I put your talk at the beginning. That's a great way to set the stage for everybody else who will talk about specific models. Questions for Lior? So let me warm up the room with one starting question. So, obviously people will apply machine learning to Rubin data fine, that's obvious. Do you think we can prepare our tools with precursor surveys? For example, in the time domain, we're doing a lot with ZTF to develop models, but ZTF is radically different in some aspects from Rubin. It has 2 bands, 3 in some cases, and Rubin has many more. How far do you think we can go with building models on precursor data sets to then maybe fine tune them with Rubin, or are we gonna need to like redesign it when Rubin comes?
That's a fantastic question. I think that's the $1 million question. How far can we go with defending against that? And we can go some way, but right now, the way those neural networks with the technology that we have right now, they're so unintuitive that's all we have is empirical. We can only use them empirically, and we're limited in what we can do empirically. We need formal models to prove them formally, and we're not there yet. Empirically, we can correct for all kind of things. We can think of what can go wrong. And we'll always be left with the question, did we think of everything possible that can go wrong? And for everything that we found in those catalogs, it's always be somewhere in the background. Is it something in the way the data was prepared? Is it something in the neural network that is too complex to identify? It's always going to be there. So I think there is we're in the middle of the expedition.
Thank you, Lior. Anybody else has a question? Willow.
So that was a really interesting talk. So I'm sorry if I'm asking you to repeat yourself, but just the whole bit about identifying COVID and certain things from those x-rays based off of the square in the corner, that's like a huge problem, right?
There it is.
Yeah, okay, could you just like talk a little bit, like, could you hypothesize about what's going wrong with
Absolutely.
these?
No, absolutely. First of all, it is a huge problem because those papers that I showed, there's not like something that I found somewhere. These are papers that were cited thousands of times, sometimes tens of thousands of times, and people were just using them naively. What could go wrong? So one of the immediate things that I know could go wrong is it identifies the source rather than it identifies the data, what you want it to identify. And so if, for instance, in the X-ray, what I think happened, I cannot prove it because I don't have access to the original data to the whole track. But what I think is that the X-rays that were positive came from one source, or most of them. The X-rays that were negative came from a different source or a bunch of different sources. And the deep neural network just identified the differences between the sources rather than the differences between the clinical condition. The same with the face data set, that it identified the source was the same. It was all done in the same lab, but it identified the people coming from a different session because you need to bring one person to take multiple images. They're not going to call a person over time and time again. They're going to call the person one time and take all the images in one session. And then it identifies the imaging session and even small differences in the lighting condition, even the temperature on the CCD when the image is taken, and the deep neural network can identify that as different. They can pick it up, and they give you the impression it identifies the face, but it identifies something completely different. It identifies the session. And I have a lot of more other examples. I just had 7 minutes, but it can go really far.
Thank you, Lior. That's all the time that we have for questions. But again, we will have a discussion hopefully at the end if everybody takes the time. So next speaker in the room is Siddharth Chaini, and here is your presentation.
Thank you. All right, so hello everyone. My name is Siddharth Chaini, aka Sid Chaini, and I'm a third-year PhD student at the University of Delaware, where I'm working with Fed. And today I'm going to be talking about DistClassiPy, which is a new distance-based classifier we've developed, and how we've been using it to classify light curves. So two particularly key challenges in the Rubin era are that firstly, only a small fraction of objects can be observed spectroscopically. And secondly, the high volume of data requires full automation of classification. And so it's important that we have to rely on, photometric classification with machine learning. And it is in this context that we've been working on developing this method and package called DistClassiPy, which is open source, and the whole goal is that we use different distance metrics to try and classify light curves. So most of my talk is based on this paper, which we just published earlier this month. And in this paper, we classified variable stars from the ZTF DR15, data release 15, with state-of-the-art accuracy, significant computational gains, augmented interpretability, and the ability to customize it to your problem. So I will talk a bit more about each of these points later on. But first, let me describe what the classification algorithm itself is doing. And I want to make it clear that the algorithm is fairly simple and straightforward. So suppose I have two classes, and I have two features for these two classes, and this is what my training set looks like. So what we're doing is that we're looking at the centroids of these classes, and then once we have a test object, we can calculate the distance of this test object to each of those centroid points, and then the nearest class is then chosen as the prediction. So this example is, I chose this example to paint a very illustrative picture, and it's in 2 dimensions, but we're doing this in higher dimensions. But even then, the algorithm itself is not particularly difficult. But when I calculated the distance in this picture here, I used the Euclidean distance. But the key innovation we've been doing is we've been looking at what happens if we change the kind of distance being used to measure the distance between your test point and the classes. And so that brings me to, let me briefly talk about what a distance is then. And so a distance is basically a quantity that tells us how similar two objects are. And a lot of math has been done into this. And basically, mathematically, we can define a distance to be a rule that obeys these 3 axioms. Firstly is the identity of indiscernibles. Second is the symmetry. Third is triangle inequality. And so basically, any rule or any function that obeys these 3 axioms is a valid distance metric. And so a couple of examples of these. So the first one is the Euclidean distance, which is something that's fairly intuitive and obvious to all of us. Makes sense. But the second one here I have here is the Clark distance metric, which again, its form and structure is very different from the Euclidean distance metric. But because it still obeys these 3 axioms, it is a very valid distance metric. So it's a very valid way of measuring distance between points. So we can also try and get a feel of what this distance space looks like. And to do that, I visualized it by looking at the loci of a central point 5, 5. So that is, I looked at all equidistant points from the center point here, 5, 5. And in the case of the Euclidean distance, we know that these are just concentric circles. In case of the Clark distance metric, this is what it looks like. So you can see that there are still concentric lines, but they're no longer circles. And so you can just sort of get a feel of how a different distance metric seems to be warping the space. And in this case, if you go in one direction, your distance changes much faster than if you go in the other direction. And so what we've been doing is we took 18 different distance metrics that have been worked on throughout literature over the past few decades and so on. And we wanted to see, can we use the different properties which these distance metrics have? And can we leverage those properties to try and classify light curves? So here is a plot of 15 of the distance metrics we used. And you can just you can see and get a feel of how different some of them really are. For example, in the bottom left corner here, the meal distance metric, the distance only changes if we move in one direction, but not in the other direction. And I do want to add that this is a 2D representation and we're doing this in higher dimensions. But yeah, so just to get a feel, this is a good visualization, I think. And so we applied this to classify light curves from the ZTF DR15, and we used classifications provided by Chen et al. And the catalog itself consists of around 780,000 variable stars over 10 classes in 2 filters. And then to develop and test our methodology, we looked at 3 different classification scenarios in this data set. So the first one was a 1 versus rest classifier. The second one was a binary classifier. And the third one was a multi-class classifier, where we looked at different subsets of objects of eclipsing variables, rotating variables, and pulsating variables. And then we also did some pre-processing where we extracted some features, dropped some redundant features, and then we rebalanced our data set. But you can read our paper for more details. And finally, we were left with 500 objects with 31 features. And so we found out that our method performs really well, and as well as a random forest, which is the state of the art for especially feature-based classification in this domain. And these are, so for all three subcategories of classifications, we were able to match the performance of a random forest within the error margins. So that's good, but then what do we do different? So it is much faster than a random forest. So DistClassiPy is often, depending on the size of the data set, at least 1 order of magnitude faster, and sometimes even 2 orders of magnitude faster in terms of time taken. So something like 0.1 seconds versus 12 seconds for large data sets. But moreover, we also perform something called sequential feature selection, which helps make our results more interpretable. And we do this by looking at what can we reduce our dimensionality even further. And so in case of Canberra metric here, we found out that just as low as 3 features give us really good results. And this is great because once we have 3 features, that's even faster to compute. But then apart from that, we also know exactly what features are going in. So we always know what's going on. And finally, a really key important point in this case, I think, is the tailorability of this method, where we can sort of choose a distance metric that works best for this method, depending on the kind of object you're interested in. So for example, here I have a data set that's split into 4 quantiles based on the period. So something like Canberra works really well for low period objects, but something like the meal works really well for high periodicity objects. So right now I'm expanding my work to look at transients, and because this method is independent of feature extraction, we're looking at different feature extraction methods involving a neural process and autoencoder. And I'm also interested in looking at anomalies, and that's also something I'm working on. But before I conclude, I just want to say that this method is open source. It's available on PyPI, so feel free to try it out, and please reach out to me if you have any suggestions and questions, comments. Thank you.
Thank you. 12 minutes for questions. And don't make me ask a question because it's my students.
So my question is kind of what you are talking here about the end, extending these to other things. So let's say I want to do something similar, but with images and not like curves. And I have some way to extract features from images and throw this into your distance space.
Yeah.
How much in your experimentation do you see, just I'm trying to understand what distance metric works best for what thing. Is it tied more to the task you're doing, more to the data you're doing, or to the features, or it's just a matter of testing it out? So
I think it depends on all of those. So we just did a data-driven approach because honestly, the big issue is that it's difficult to, so the ideal scenario would be to have a physics-informed distance metric, which really separates your 2 features, and there's some physical reasoning behind it. But I think like in this case, because it's not so trivial in these higher dimensional spaces, a data-driven approach is the best approach to go about it. But if you have features, you can definitely give this a go. And we have designed this on scikit-learn, so the syntax itself should be very straightforward. So please give it a go.
thank you.
Thank you.
Perhaps one quick question while I set up for the next speaker. Over there.
You said that you're working on transients, including transients. What sort? What sort of transients do you want to include?
Yeah, so right now I'm looking at the plastic data, and I also want to look at the elastic data just as a way to sort of start thinking about how LSST is different from ZTF, which, like Fred mentioned, we have 6 filters instead of 2. And so right now I'm taking these demo data sets in a way, right, plastic and elastic, and then I want to build methodology related to that. And then once Ruben does go live, I hope to sort of use it.
Thank you.
Thank you.
Thank you again, Sid.
Thanks so much.
The next speaker is Somayeh Khakpash, who's a Catalyst Fellow from Gregory University.
Hi everyone, it's great to be here. So I'm going to talk about this project I've been doing over the past 2 years, automatic generation magnification maps for lens quasars and supernova using deep learning. So I'm going to give you a brief overview of what the problem is and what is our way of solving this problem. So in strong lensing, when we have a quasar that is lens and we get multiple images of the quasar, each of these images are going through a different part of the sky on the lensing galaxy and through a different distribution of the stars. And therefore, each of these images are also micro lens. So if you watch them over time, what you see the micro lensing variability that is caused by the the compact object within that a small patch of sky on the lensing galaxy where the image has gone through. And we get a light curve for each of these images, and we see variability that is the same in all of the images, which is the intrinsic variability of the quasar, but we also see the microlensing variability, which is different for each of the images because they go through different parts of the lensing galaxy. And we want to basically model the microlensing variability when we see these light curves. And why do we care about it? Because we can study the structure of the quasar, we can study the mass distribution of the lensing galaxy. We can also get better measurements of the time delays by removing the microlensing variability from the light curves. And in order to do that, we need something called a magnification map, which is a theoretical map that tells us, given a distribution of compact objects and smooth dark matters, how would the brightness of a source would change if it goes through this patch, a small patch of sky on the lensing galaxy. And it's described by all these like bright areas and dim areas, and that tells us, depending on what the trajectory of the source is, how would the brightness of the source change? And then we can model the microlensing variability. This magnification map depends on three main parameters: kappa, gamma, and S. The total mass in that small part of the sky, this external shear, and the fraction of a smooth dark matter to the total matter. And the problem is that when we have the light curve, we need to look at as many magnification maps as possible in order to pin down what the parameter kappa, gamma, S is. And these maps are computationally expensive to generate, so we need to find an efficient way to search through the parameter space and find the best parameters for the lensing galaxy. So the way we're doing this is that we're using an autoencoder, which is a type of deep learning model here. And we have trained it on 12,000 pre-computed magnification maps. And what it does is it takes the input maps, it shrinks them down into some lower dimension, and then the decoder, the second part, is taking the low dimension and then reconstructs the original maps. And what we're doing here basically is we're learning those patterns in the magnification maps, and we're learning how to reconstruct them at this point. And that compressed version in the middle is called the latent space representation, which, if the reconstruction goes well, that should contain the most important features of the maps, including the parameters that were used to generate the maps. So at this point, this is an example of the autoencoder reconstructing an example map. The first row is the original map. The second row is the autoencoder map. And we have the light curves generated from the original map and the autoencoder map. And we can see the differences and similarities between these light curves. But the question is that we see this visually, but how can we quantitatively say that these reconstructed maps or new maps are valid physical maps? How can we trust them? How can we actually use them instead of the original maps? So we need metrics to tell us if these maps are really, we can trust them and use them instead of the original maps. And this is a real challenge because theoretically, there aren't any ways that tell you, if you're given a map, what is the kappa gamma S of that map? So it's really hard to really go from the maps back to the kappa gamma S. So what we did is that we used some metrics using different other areas, like the FID score, which is using computer vision to tell us if a generated image is authentic. And so what we use here is that with the FID score, it tells us if the statistical features in the output maps are representatives of the statistical features in the input map. And then we compare that for different trials, for different structures of the autoencoder with different parameters, and we can tell like how these results compare. And we also look at the similarities in the map pixel values, and that's also very, that we also use that to compare the different structures of the autoencoder. What we also do is that we look at the similarities between the light curves generated from the true maps and the autoencoder maps. The way we do it is that we generate random maps from the true map and the autoencoder map. Then we compare those random maps with one peaked light curve from the true map. And then we look at the minimum light curve distance. We pick the best light curve. You can see here different trajectories for the random maps. The green one is the peaked light curve where we compare that with the other ones. And the dark blue one is the closest one that is chosen. And then we repeat this step 1,000 times for different peaked light curves to get a distribution of minimum light curve distances. And basically what we do is that we compare these two distributions for the true map and the autoencoder map. We want to see if the overall statistics of the light curves are the same for different maps. And this is a single map, but we repeat that for maps across the parameter space of kappa and gamma. And we want to see if these distributions are the same. We're using violin plots to compare these two distributions for each of these maps. So you can see maps across the parameter space of gamma and kappa. You can see that the values of the minimum light curve distances are different because the geometry, because the features of the maps in different regions are different. But the similarities between the two distributions are, the two distributions are very similar across the parameter space. And then finally, we have this autoencoder which can reconstruct all these maps. But if you give it the right member of the latent space representation, the autoencoder can generate a new map for you. So what we're working on is to basically connect the latent space representation to the parameters kappa, gamma, s to generate new examples of the latent space representation and use that to generate the new maps and then evaluate that using our own metrics. Yeah, and then finally, when we have this trained model, we can generate a map on a single CPU in less than a second because it's already trained. And we can incorporate it into the analysis of the light curves, trying to look through the parameter space more efficiently and fast. And eventually testing all these metrics that we have developed. And this is an image of myself that is given to the trained autoencoder, and it has reconstructed me as a map, magnification map. And you can also see me in the latent space.
Thank you so much. Hi.
Nice talk, thank you. What is the angular scale of your map compared to the angular distance between the various different sources of the different quasar images?
So these maps are 20. So the stars that are basically assumed for these maps are one solar mass. So all of these stars that are basically assumed to generate these maps are one solar mass. And the scale of the map is 25 by 25 Einstein radius of such a star. And then the source can, the size of the source then can be as large as 0.6 Einstein radius, for instance, or as small as like 0.1. So in that range, it's the most common for the quasars. For the supernova, I think it can get bigger than that.
So there should be some information, but delayed in time, between the different quasar images. I'm wondering if that's possible to do. It's a correlation that's introduced by the different time delays for each image.
Yeah, I guess so.
And one could require that, because that's the physics tells you that must happen. There's a different time delay for the light from each one of the images experiences.
Well, that depends on like what the.
But the
duration
original
is.
maps, in the original maps, only one map per star field is produced with different values. Like they don't do time series of maps.
Well, not like we don't do that. Like people do that, but at this point, we're mainly focused on like generating the maps, and then be able to then test various maps for like basically find the best trajectory that would generate a light curve. But yeah, but people, yeah.
But not in the
Yeah, no.
not in the maps that were
yeah.
used for training.
Yeah.
Another question, perhaps really quick before we switch? Siddharth.
This is great, by the way, thank you. When you calculate the L2 distance between the light curve, so can you tell me what your light curve, like how well sampled is your light curve and what does that look like?
So these light curves are like 100 data points across a long time. Like it's like the cadence is like every few weeks in this case, but it's usually enough for the microlink variability in the quasar because the time scale is usually very long.
Okay, but then when you're comparing two light curves, are they like very similarly sampled? And is
Yeah,
it easy?
they
Okay,
are. Yes, they
Okay,
are
okay,
in
okay.
this case. Yeah.
Gotcha. Thank you.
Excellent. Thanks again, Somayeh. Willow Fortino.
Hello, everyone. Hi, my name is Willow, and today I'm going to talk to you about spectral classification of supernova. So if you're interested in supernova and spectral things and also classification techniques, inferential AI, then please listen up. Specifically, I'm talking about the viability of transformers on spectral data, on one-dimensional data. So let's get started. First of all, what is the task? The task is to classify supernova subtypes. There are about 16 different types. Most of them are here. Our data set consists of about 4,000 spectra from various different sources. These are generally high signal to noise ratio spectra. The first 3 citations you see here, the first 4 are mainly stripped envelope supernova, so we have a good representation of those. But of course, the majority of supernova spectra that you see are going to be type 1A and ones that are commonly mistaken for 1A, like the other subtypes of 1As. Now, the goal is to use a transformer. I'll talk a little bit more about what transformers are, but they're the cutting edge of machine learning technology, if you will. If you're familiar with ChatGPT, then GPT stands for Generative Pre-trained Transformer, I think. So they're all over the news everywhere, and we want to see if they can work with spectral data. And of course, we also want to see how they compare, how they stack up to existing machine learning models for supernova classification. And the first thing that we did was take a look at DASH. DASH stands for Deep Automated Supernova Host Classifier. Came out in 2019. And this was the confusion matrix that they posted. So just to give you, just to get you a bit familiar about what you're looking at here, you're seeing that we've got the 16 different supernova types along the columns and the rows. And along the diagonals in blue, you want that to be as close to 1 as possible, representing a high accuracy. So this is what they posted, but DASH doesn't just classify supernova subtype. DASH also classifies supernova age, or also known as Epoch. It also gives a redshift estimate. It also gives a host galaxy classification as well. So it does a lot. Something that we identified that this paper did is they used some of the spectra from the same supernova in both the testing and the training set, which means that if you want to be able to classify a brand new supernova that you've never seen before, then DASH isn't going to perform as well. And so if you fix that, this is what the new confusion matrix looks like. You can see that a lot of the less common classes performance degrades quite substantially. Just taking a look at one peculiar in the middle here, we're not able to classify it at all. Same thing with 1A peculiars, type 2Ns down at the bottom right as well. So regardless of how good this is kind of our new benchmark that we're going to compare our preliminary results that we have with transformers. So what is a transformer? What are we doing here? Well, I don't have time to get into everything about what a transformer is, but it came out in Vaswani et al. 2017, this really important paper, and this is figure 1 from that paper. The important thing here is that a transformer is a generative AI model. It's designed to work for natural language processing. It's designed to ingest human words, and it's designed to output also human words as opposed to other animals. But we don't want to do that. We want to use this for inferential AI for classification. So what we do is we remove all of this stuff. This was the decoder on the right here. And we add this, what we call a feed forward classification head. This is pretty standard what people are trying to do with transformers these days. Okay, so for the transformer classifier, there's three really important things that I want to point out. The first is the input embedding and the positional encoding. So the input embedding is a process in natural language processing that takes your sentence and embeds it into a numerical space, into a very high dimensional numerical space. This is really crucial because transformers, I don't have time to get into it, but transformers need multi-dimensional data. Of course, spectra is one-dimensional data. We have flux and wavelength. And so that poses a problem. The second thing is the positional encoding. Because of the way the core of the transformer works, essentially the transformer is agnostic to the positions of your inputs. So you need to give it some information about the position of your inputs, and that's where the positional encoding comes in. This shouldn't make any sense to you. This is a bunch of sines and cosines that are varying along one axis and also along another axis, and you literally just add this to your inputs. That is the positional encoding. And it's designed to help the transformer learn the positions of your inputs. Now, finally, the most important thing here is the multi-headed attention, or just the attention mechanism. This is a self-similarity operation, essentially, and it tells, and what it does is it learns the relationship between your inputs. So it relearns the relationship between the words in the sentence. That's why it's so good. That's why ChatGPT is so good at producing convincing speech. So what are the challenges that we have here? Well, the first one is that our data set is extremely imbalanced. We have about 50% of the data is just one of the 16 classes, Supernova, 1A normal. And we also have a relatively small data set of just 4,000 spectra total. For machine learning, that's pitiful. Also, for some of these really uncommon classes, we only have less than 5 supernova total, less than 15 spectra from those 5 supernova. So that just makes machine learning in general really difficult. So you're going to see that reflected in the confusion matrix. We also identify probably some label noise between the similar classes. The idea is that these supernova exist on a continuum, right? Of the progenitor mass, that's a continuum, the angular momentum, the total energy of the system, how much circumstellar material there is. This is all a continuum, and we're putting these into discrete bins. There's going to be some label noise, right? There's going to be some mislabeling of these. And finally, the most important thing that I mentioned before is that transformers were not designed for one-dimensional data. So how do we overcome this? Well, we're taking a look at existing methods, specifically astroconformer, this paper. This is transformers on stellar light curves. So it's not spectral data, but it's similar. It's one-dimensional data. They have a really clever mechanism for doing this input embedding, and then, which is essentially an upsampling mechanism with its own neural network. It's a bit clever and too much to get into right now. And then there's also this rotary positional encoding, which is different than the positional encoding from before, but it's similar. And you can see here's the confusion matrix when we have this rotary positional encoding. This doesn't look as good as before, but these are preliminary results. And then here is the confusion matrix without any positional encoding. This is kind of what's demonstrating, and maybe I didn't drive this home, is that people, when you Google transformer-based classifiers, the positional encoding is not emphasized, and it really, really should be, and I hope this demonstrates that. So thank you very much. Please give me your questions.
Question about the classification of supernovae. The thing is, like, for all the type 1A supernovae, like if you are making just them in one single class, will that just improve your classification prediction? Because like between a 91 BG and a 91T and a normal supernovae, like it's more like a continuum, and you are going in a non-linear physics, I guess.
Yeah.
So like I guess this is more or less the same type of objects. Like, so if you were trying to just put that as just one single class, and it will increase your data set, I mean, it will not be better for the classification, or
Right. Yeah. So the question is, why can't we just aggregate these larger types into broader types? And you totally can. And you definitely will get better results. It's a far easier problem. Yeah, it's actually really frustrating how easy that problem is compared to this. But ultimately, that's totally valid. And the only reason that we do it this way is because we want to be able to see what the performance is on all of these. These are approximately the most, numerous or a proxy for interesting supernova subtypes that are in the field. And so that's the only reason, but you're entirely right that aggregating these types will give you a more reliable model easier.
Also, like, if I remember, like the way you classify the spectra for supernovae, like this is using like I forgot what it's called, like but this is like the Blondin software, like
SNID, supernova identification.
Yes, but like so if there is a bias in this one, it will propagate to this one also.
That's correct, yeah. So that's another thing that I mentioned before about the label noise is that SNID. I don't know how everybody feels about SNID in this room, but I think it's safe to say that it's controversial among some. That's certainly a problem. That SNID is kind of the only, apart from human expert identification, SNID is the only way we have to verify these supernova subtypes to train these types of models, and there certainly is bias in that.
Thank Willow again. You're up. And this one. Tiny phone. Presentation mode. Jesus, that's really tight. Minute. Oh, wait. If anybody has suggestions on how to turn this into a presentation, maybe download. Oh, view. How about we download it and then open it up? Okay, we still kind of have the same problem. And just a little bit larger. That.
Is there a desktop PDF view or something like that? Is there Adobe or something like that?
I have preview because this is a Mac. You know what? Sorry, I'm gonna remove this so I can actually see what we're looking at here. What is this? This one? Preview. And I still don't know how to do this, but I can hide the sidebar. Good enough? All right. And then give me a second, I'm gonna screen share. Again, yes, see my hands. Thank you. You're good. I think you're good.
Okay,
Yes.
so can you hear me in backside? Okay, great. Hello, my name is Gregory. Actually, it is really it is a first time presentation since defending my PhD 3 weeks ago. Which is thank you. So I'm gonna introduce. It is really exciting to introduce the our new facility. The name is 7-dimensional telescope. How to classify the various types of transient using the single epoch spectra and its distributions from our facility. As we know, we are living in the era of the gravitation wave multi-messenger astronomy, right? So if the compact projector systems including more than one neutron star, then we can expect both signals, the gravitation wave and the kilonova, which is the electromagnetic counterpart gravitation wave source. So the GW17OS17 is it is the prime event, and also it is the only and one event still. Thanks to this event, we can study the peaks of kilonova and the environment of gravitation wave source. And also we can see some possibilities to solve one of the most controversial problem in the cosmology. Anyway, the electromagnetic counterpart to identify the kilonova is the key to the successful gravitation wave multidimensional astronomy, because by pinpointing the exact position of the gravitation wave source. But there are so many difficulties to identify the electromagnetic counterpart during the gravitation wave follow observation. So one of them is classification. No matter how we can, no matter how we can get a very well localized gravitation wave event, there's so many kilonova contaminants, and most of them are supernovae, various types of supernovae. So to classify them, we usually use those two methodologies. First one is spectroscopy. The other one is to acquire the light curve of transients. The spectroscopy is one of the most prominent method, but it is expensive and it is limited by the brightness. In contrast, the light curve is a cost-effective but less effective than spectroscopy, and also it requires multi-epoch data. That means we may lose some important data of the transient. So we need some synergistic approach by combining those two methodologies. And also, this is the Lubin workshop. So we all are waiting for the upcoming era of the Lubin. So the more than 10 million transient alerts per each night are expected, and there will be some rare transients like kilonova with or without the gravitation wave trigger. So anyway, we have very limited observational resource, and we need to further analyze the transient by following up those kind of transient alerts. So for the efficient follow observation, we need the classification is very essential process. So I want to introduce the new facilities, the 7-dimensional telescope. And the project PI is Professor Myung-Shin, and I'm in charge of those three tasks. I want to share these three magic numbers about the 7-dimensional telescope. First, we have 20.5 meter telescopes in the same area, and we use the 40 medium band filters. The medium meanings, the meaning of the medium is that our bandwidth of filters are only 25 nanometer. Each telescope has a wide field of view, so we can easily cover the sky localization of gravitation wave source. And this is our comparison of the filters with broadband and our medium band filters. Each telescope, we keep 2 filters for each. And also, we can flexibly operate our 20 independent telescopes, so we can use many observational mode. And this field of view is quite comparable with the Lubin LSST's field of view. So this is the observed real imaging data from 7-dimensional telescope. If we observe this field like that, then we can get the low resolution spectral and distributions of all detected sources in the image. This is our main strong idea. So let's imagine if we just observe some transients with a few broadbands, then it is really hard to classify them, because the broadband remove out some very detailed spectral features. But if we observe the same transient with our 7-dimensional telescope, then it is easily say, oh, it should be the kilonova or something like that. So our strategy is like this. I'm gonna classify the transient using the single epoch SED classifier, and yeah, and training data is like this. So I use the simulated synthetic magnitudes because the 7DT has there is no transient data yet. So, and also my main focus is to identify the kilonova, but theoretical models are still weakly constrained these parameter spaces. So instead, I only train the various types of supernova, and I'm gonna identify the kilonova as an anomaly. Okay, let's skip this. So I compiled many spectra of various types of supernovae from the Open Supernova catalog. I can compile about 5,000 spectra, and I increased the number of the samples through the data augmentation. So using the 39 colors as an input feature, I trained the light GBM model. Then I can train the model to give us some probability for each for our classes. Here's the performance. Performance is not bad, but still F1's some Lior scores are a little bit lower than others because 1A peculiar is really hard to classify. I mean, hard to correctly classify. So this is the how I want to explain the how I identify the kilonova as an anomaly. So if the probability for some input sample for various types of supernovae is lower than some threshold, then I can say this is a kilonova. So in summary, if I set some threshold like this, then supernova. Okay, sorry about that. Okay. Okay. Sorry about that. Anyway, if I set some threshold like this, then this model can classify the kilonova with a few supernova contaminants. So I applied the Lior data and it works well. And this is a summary. So thank you for listening.
Thank you.
Going back to the curves of the threshold,
Yeah.
is your
Thank you.
data simulated data? Because these curves can change depending on the data subsets. So
Yeah.
for example, I think this classifier should not be calibrated, because if it's a calibrated, it would be a curve that would go like linearly. So I was wondering how you were gonna set these thresholds to have the purity of kilonova that you want to have.
Yeah, actually, this is the most critical limitation on my study because I use the kilonova samples from the only real data, the GW17 or 17. So it is really biased threshold. So maybe I should think about the threshold, but we have only one sample. So using this only sample, we can freely just set the threshold considering the lower supernova contaminants like this. So,
but just a suggestion: when you have more data, true data, you can also calibrate your curves as such that the threshold, it means that the fraction of objects that they will find. So, for example, if you set the threshold to 50%, if your classifier is calibrated, it means that you have 50% of finding a kilonova.
So okay, thank you. So maybe we can talk later.
Let's thank Gregory again. Flash our hands. There we go. Are you still screen sharing? Yes.
So hi everyone, I'm Shar. I'm the TVS Fast Transient Subgroup Coordinator, and I'm a graduate student at the University of Delaware. The work I'm going to talk about today is done in collaboration with Igor Andreone, who's over there, as well as Fed and Ashish Mahal. Okay, so to give you an idea of where we're going today, I know that this is the machine learning session. So first I'm going to convince you that fast transients are really cool. And then I'm going to mention what I used to study them, which is continuous readout mode data and a convolutional neural network. It's not a particularly innovative convolutional neural network, so don't get excited about that. But do get excited about the stuff that it found, which so far is a lot of non-astrophysical transients and possibly a real astrophysical transient, but we'll get there at the end. So that we're all on the same page, astrophysical transients are anything whose brightness changes on human observable timescales. And often these are extreme phenomena that contest fundamental physics at a higher energy scale than we could ever see on Earth, because if you had a star exploding on Earth, that would be a real problem. It's also a realm where you can find new and entirely unexpected phenomena. You don't need to know what you're looking for when you find it. And that means that there's a lot of potential for discovery in this space. So I want to present this map of all known optical transients as of this year, 2024. You can see on the y-axis, we have the magnitude, so the brightness that it gets at its maximum. And on the x-axis, we have the characteristic time scale, so how long it takes it to vary. And that's in days, so right around the middle, we have like 1 day. And the right-hand side is pretty well filled in, but you'll notice there really isn't very much on the left-hand side of things that are varying in less than a day. And that is not because physically we expect that nothing can change in less than a day. Actually, it's just because it's really hard to look at stuff that's changing that fast with a regular telescope, because a CCD requires seconds or minutes for exposure and readout. However, these are some of the objects that are expected to vary in that realm of parameter space. So anything from occultations of solar system objects, so like something passing in front of a star, cataclysmic variable stars, blazars, potentially even the optical counterpart to fast radio bursts, could vary in the left-hand side of that plot that's pretty empty right now. So to get around that constraint, I am looking at continuous readout mode time series data, which you can see in the background of this slide. These like faint horizontal stripes, believe it or not, those are stars. The x-axis here is time, the y-axis is position, and we get a very fine time resolution with this mode of data. This is taken with a regular CCD camera, but you leave the shutter open during readout and exposing, which means that as the charges are being like dragged off to one side to get read out, it's still continuously taking more data. So it looks like this, and it looks like this, and basically it ends up with all of the stars or galaxies or whatever looking like those streaks that you saw in the last image. Here is zoom in on one of those star streaks. So on the top, we can see exactly what we get off the CCD. On the bottom, you can see that translated into a time series because everyone would rather look at a time series. And then on the left-hand side, we just have the like full width of one image, and on the right-hand side, it's zoomed in so you can see it a little better. And for all of the plots I'll show you, I plot with Poisson error for the counts, and then also a standard deviation error just to get a sense of the variability of it. This is real data. This is implanted data. So if we had something varying at this very short time scale of, I don't know, like 3 milliseconds or like 15 milliseconds, this is what it would look like. on the left-hand side in the full streak, it would just be like this tiny little blip. On the right-hand side, if we zoom in, we can see this like Gaussian-ish brightening. And then this is what that would look like on the time series. So my very kind collaborators have taken a bunch of data in this readout mode. We currently have about 350 gigabytes that we're working with. And remember, the resolution is like 3 microseconds. So between all the streaks, we have about 1 billion stellar data points, which is why we need to use deep learning for this problem, in addition to the fact that it's such an uncommon data type, like there aren't pipelines in place already to figure out what we're looking at. And we're looking for very rare signatures of just a few data points. These are the fields we've observed so far. So this is my beautiful CNN that I use to find stuff in that data. It classifies each pixel as the background or a star streak or a transient. It looks for predetermined transient behavior. Here's some of the stuff it found. So one of the things that it found that is not an astrophysical source, which I realize you can't really see. So imagine on the top where you have those horizontal lines, there's one that's diagonal too. That means that something's moving. So like a satellite transit or an asteroid or anything else that's moving and like intersects with a star results in this kind of a light curve that we don't really care about because it's not astrophysical. We found a few of those in our data. What we found a lot of are cosmic rays. So basically a charged particle that hits the CCD, and then it shows up as like one or a small number of pixels that brighten kind of randomly, not correlated with like a star or anything, like there's no streak here. And about 68% of the CNN detections are cosmic rays. So a lot of work so far has gone into reducing those in post-processing and figuring out what we're left with. Now, one of the things that we may be left with is this very cool and fun looking curve here, which at a very preliminary glance looks like it could be an occultation, which would be like a Kuiper belt object passing in front of a star. What we expect that signature to look like is shown on the left there. And it has like a diffraction effect, which is why it looks all wiggly. Now, again, this is a very preliminary result. I'm not claiming that that's definitely what we found, but I am claiming that we can find stuff that looks like that using this continuous readout mode and the data that we have. And then I also, so all of that data that I have so far is on ZTF, but a similar observing mode was proposed for LSST by David Thomas in this 2018 white paper, where essentially you would turn off the tracking and then just like let all the stars turn into little trails. And then you could get some of that time series data in that way as well. Thank you.
Sure.
There's one in.
Oh, there's a question on that? Yeah. Can you?
So they have to.
Uh,
Yeah. Oh, sorry.
Oh.
Yeah.
You have claps on Slack.
I appreciate it.
Thank you for the clap. Questions in the room or on the channel?
Yeah.
Please.
So if you go in this mode, are you going to start seeing charge transfer inefficiencies and pockets, because that will give you exactly the same type of effects, which are electrons pop up like cosmics?
Yeah, honestly, that's probably what some of them are. That's a great point.
There is a mode that is used in engineering, right, to run the charger.
Yeah, absolutely. Yeah, yeah.
It could be some of those. I cut them out, whatever they were. Also, possibly some of them are glints from satellites. But if it isn't on a pre-existing like star streak, then I basically ignored it. Is there another question?
There is one general on this slide.
Do you want to read it? So there's a question on chat that says to get input from multiple sources, those who may be novices with machine learning, can you suggest a good resource or online course to start learning? Why don't you?
Yeah, actually, I'm gonna point that back to Sid, who I know has like a YouTube series of, it's about machine learning. I don't remember what it's called.
Oh, the 3 blue, 1 brown one?
3 blue, 1
And
brown.
that's like wait, that's like a good intro to neural networks.
Mhm.
Well, let me pitch maybe since Andy is here, Andy and Shelko's and book called Machine Learning in Astrophysics. That might be a good resource that we probably do, which is, you know, really done by people that are involved in Rubin. So might even be biased to things that you might be able to do with Rubin.
Yeah, and if anyone else has a good resource, please put it in that Slack thread, because I'm sure there's lots more out
I have gone through that book. It's amazing. Highly recommend.
there.
All right, we have two more. Thank you, Shar. Two lightning talks. I think we can take the first one from Zoom. Priyanka, are you online?
Audible?
Priyanka is online. Priyanka Gawan.
Can you hear me?
Oh, yes, we can hear you. Excellent. Would you wanna, do you wanna go? Are you ready? I'm gonna stop sharing my screen so you can share yours. And while Priyanka gets ready, these are talks associated to posters. So please make sure you afterwards go and check out the poster.
That's that.
Yeah, you good, whenever you're ready.
Hi everyone, I'm Priyanka. I'm a PhD student at IUCA, India. I have been working on modeling strong lenses using machine learning techniques such as convolutional neural networks. Conventional lens modeling methods are quite time and resource consuming, require sophisticated lens modeling code, and we need fast and automated methods to analyze the heap of lenses expected from servers like LSST. Aim of this work is to analyze images of strong lenses obtained from ground-based surveys such as Epoch and LSST in order to model them. These images are limited in quality due to low pixel resolution and atmospheric blurring, which leads to blending of the lens background arcs with the foreground lens galaxy, making it further difficult to analyze. We have used a simple CNN as shown in this figure. We input GRI band images of these lenses, and we expect the network to output lens mass model parameters such as Einstein angle, axis ratio, and position angle. We train our network on around 60,000 simulated images of select lenses. And when tested on the simulated test sample, our network can recover these parameters reasonably well. This is Einstein angle, this axis ratio, this position angle. On the y-axis, it's the network prediction. On the x-axis, it's the two parameters, and here is the sample image. When we test this model on the real Sugoi lenses, we first process the Sugoi lenses with a pipeline called data lens in order to remove the central lens light to make the background arcs detectable. And this pipeline also gives some rough estimation of these parameters, which we can use to compare our network predictions with. So here in this panel, we have also compared the results on a sample of Sugoi lenses with some existing studies and literature. And we find that Einstein angle is kind of the robust parameter to estimate because it just depends on the distances, where position angle and axis ratio depend on the actual configuration. So these are the trickier parameters. So we find disagreement between these different methods, especially in axis ratio and position angle. So all of these other three methods are actually MCMC, sophisticated MCMC modeling codes, but still we can see that there's disagreement between these codes, and we are trying to understand this discrepancy. Again, the unavailability of truth for this real Sugoi lenses makes it difficult to actually gauge the performance of our network on these. In future, we plan to add more length and source parameters along with their uncertainties and apply a similar technique to mock LSST data. The details of this work can be found in this paper on the slide, and you can also email me on this email. Thank you.
Thank you, Priyanka. Time, and also in the interest of making sure that you will actually go and see the poster where it's on the web space dedicated for it. Let's put questions on Slack and also add your questions after you have actually looked at the poster carefully. And Priyanka, if you can stop screen sharing, I can start sharing the next poster. So the last talk is Biswas. And this is also a poster, so then go look at the poster.
Hello, everyone. I'm a PhD student at APC in Paris, and I'll be presenting to you this poster on the Madness D-Blender. So it's a project that I've been doing in Desk, and we are in the internal review, and the paper will soon be out. So what we are trying to address over here is the effect of blending. So blending happens when astrophysical sources are overlapping in our images. These are physically separated, but since they are very close along the same line of sight, tend to overlap. And what we want to do is separate these overlapping sources into their isolated components. Typically, what is done is assume some symmetry properties of these galaxies, such as like symmetry and monotonicity of the light profile and so on. But what we want to do is we want to use deep learning to learn complex priors on these galaxies and model complex morphologies. So the architectures that are used are, number one, a variational autoencoder, which compresses the data into a lower dimension space. We have already have talks on variational autoencoders today. And the second network that's used over here is a normalizing flow, which models the aggregate posterior distribution of all the galaxies in the latent space. What I show in my poster is that we can use these two models to extract very complex morphologies from blended scenes. And it works better than like traditional state-of-the-art deep blending algorithms that are out there in the market. And if I talk too much, none of you will visit my poster, so please find me in the poster session.
Perfect. How's everybody doing? A lot of talk, but they were all awesome. So I hope you have some energy left for a bit of discussion. To that end, I put on Slack, since we don't have a lot of time, we only have 5 minutes. I put on Slack a link to Slido. So I would like to ask you all to go on Slido and put in the number that I put on the Slack channel. And the prompt is, tell me in less than 3 words, what is your main concern about application of AI and machine learning to Rubin and for Rubin? And then we'll look at the Slido in about 3 minutes and we'll just see what people have put in. Let me just, so the link is slido.com and the number will be on the slides in a second. But you can find it on the Slack channel, so you can get ahead of me by just looking at the Slack channel. I will edit this to add the number. If there are technical problems and you can't do that because of technical problems, let me know. Is it working? Assuming the silence means yes. It works.
What is an ITER student?
Where?
Could you repeat
Oh.
the question?
In less than 3 words or less, what is your main concern about Rubin and AI, developing Rubin for AI, applying AI to Rubin? You can have more than one answer, but they shouldn't be combined to form a sentence that is longer than 3 words. They should be 2 independent 3-word prompts. Because otherwise, when we look at them on Slido, too long. hadn't planned on Slido because I thought we had a little bit more time, so I set up the Slido on my phone. How do I view?
Yeah.
If you all saw how small the font that is on this computer when I'm connected to the screen, you would understand my current pain. Okay, we're gonna go look at them in a second. Okay, well, that's a lot of answers. That's several more answers than the people present in the room and online. So people have more than one concerns, and that's my first statistical assessment. CCD defects, AI era. I'm not sure what that means, but I do think that the AI era is pretty scary to most of us. Bias in training, we covered that a little bit earlier in Lior's talk. Uses of acquired technical knowledge on unethical businesses. That's true. We train a lot of people on AI to, classify galaxies, and we don't really care about the privacy of galaxies, and we forget to tell them that people are not galaxies, and then they go work for the medical field and police and law enforcement and all. Very loose. Ongoing transient classification, which I think it might mean both real-time transient classification and transient classification in the presence of a growing zoo of transients, many of which we haven't seen yet. Hopefully Ruben will see many more things that we haven't seen. Overfitting, Lior helped us with that. This is longer than 3 words, so I'm gonna skip it. Another one that we heard about today a little bit at the SAC meeting is compute availability, and maybe understanding what are the resources, the computing resources that are going to be available to us. Blended data trails, assuming that I refer to the glints and satellites that we heard about in the session this morning from Tony and Meredith. Realistic training set, we discussed it briefly. I see bias in the training set is appearing a lot. I will do a word cloud of, whoa, keeps on going. GPU access, lack of causality, that's interesting. Lior, stop. I will make a word cloud because I don't know what else to do with my time. I'll make a word cloud and post it on the Slack channel for us to briefly and intuitively ingest this list of words. Thank you very much. This is the end of the machine learning and AI session.